So in this presentation, we'll go over the Bohr model of the atom. Our objectives: we will first start by using the Rydberg equation to calculate energies of light emitted and absorbed by hydrogen atoms, and then we'll describe the Bohr model of the hydrogen atom. So let's revisit line spectra. There are all the ones on the bottom there, starting with sodium, going to hydrogen, calcium, and mercury. These are discrete lines emitted, and they're characteristic for each element. Line spectra can be observed both by astronomers looking at stars and by people using arc lamps or flame tests. You've done a flame test in the lab so that you know there's a characteristic color emitted when you burn inorganic materials, especially those containing metals. So, back in the day, the scientists of the 19th century started to quantify their observations, and Johann Balmer calculated a relationship between the lines in the visible spectrum of hydrogen and the energy emitted by those lines. He used integers to get the relationship. This was kind of a big deal. Other experiments were used to get the spectral lines for hydrogen in the UV and the IR regions. And from that information, Johannes Rydberg derived an empirical equation to describe all of the lines, UV, visible, and IR. This equation can be used for any lines generated by hydrogen. So we have 1 over lambda, and lambda here is our wavelength, is equal to R infinity, which is the Rydberg constant, 1.097 times 10 to the 7th per meter, times 1 over n1 squared minus 1 over n2 squared, where n1 is less than n2. And that's important because if you do them in the wrong way, you end up with negative wavelength, which is not a thing. Definitely not a thing. We can't have negative length. All right. So this is a pretty easy concept. I mean, it's nice and simple, as most of these things tend to be. So let's try using the Rydberg equation. What is the wavelength of light emitted when a hydrogen electron goes from n equals 4 to n equals 2? I like to solve for the variable I need in the equation before plugging things in. This helps me to visualize the relationship between each of the variables. So I take the inverse of both sides, and I get wavelength is equal to 1 over the Rydberg constant times, in parentheses, 1 over n1 squared minus 1 over n2 squared. So at this point, we remember that n1 is less than n2. So even though we're going from 4 to 2, we have to use the 2 as n1 because it's smaller. So we're going to do 1 over 4 minus 1 over 16. And when we do our calculation here, we get 4.86 times 10 to the negative 7th. And that is 486 nanometers. So this will give you a positive value for your wavelength. If you flip them, if you go, oh, I'm going from 4 to 2, I should do 1 over 4 squared minus 1 over 2 squared. You are wrong, and you will get a negative number, and that does not work. The Rydberg equation only applies to emission. And emission, we're going to do final minus initial. The final state is 2, 1 over 2 squared minus 1 over 4 squared. All right, let's try a different tact here. What transmission of hydrogen emits a 92.6 nanometer line? Again, I know that the Rydberg equation is going to apply. Further, I know that 92.6 is less than 486 from the previous problem, so this is UV light, and it has a higher energy. So if it's a higher energy, we know the larger jump is probable, because there's an inverse relationship between wavelength and energy. So we want a larger jump, which will give us a smaller wavelength. All right, so we should be looking for that larger jump. And in the previous example, n was equal to 2, so let's try 2 or 1. We'll try 1 first. Okay, so at this point, I rearrange the Rydberg equation. I start with distributing the Rydberg constant, and then I subtract R infinity over n1 squared from both sides. From there, I take the inverse, and I also multiply by r infinity on both sides, and I get this fun equation here. Negative r infinity over 1 over lambda minus r infinity over n1 squared is equal to n2 squared. So if I take the square root of both sides, I will get n2. And so that's what I do. And I plug everything in, and finally n2 is equal to 8. Which kind of seems like a decent amount of work to get a relatively simple value, but that is science for you. So as these things tend to happen, another person came along and built on previous research. So Niels Bohr started with Rutherford's research saying that there's a positive nucleus surrounded by electrons. He combined it with Planck's realization that energies were quantized, and Einstein's idea that light consists of photons with energy proportional to frequency. And he said, you know what? If I make all of these assumptions, and I say that the electrons have a quantized energy associated with their orbits, and the orbits will be circular because he's still thinking classical mechanics, it could explain the origin of the lines in the hydrogen spectrum. When the electrons jump from one energy to another, they can absorb or emit in the form of light that we can observe. So Bohr showed that the Rydberg equation could be derived from first principles if you make these assumptions, where you have change in energy equal to h nu, and you have energy equal to negative k, and k is made up of constant from other physical constants, over n, and that's our integer from Planck, squared. Okay. He later explained that E equals negative kz squared over n squared, where z is the atomic number. So you can apply this to more things, but it always had to have just one electron. All right, now when he went through and he numbered the energy levels, the one that's closest to the nucleus is n equals 1, and he went up from there. You can see that on the diagram on the left. At n equals 1, the one closest to the nucleus, it has the lowest energy that the electron can take, and this is called the ground state. The radius of the ground state is given by, when n equals 1, r equals n squared over z times a naught, where a naught is the Bohr radius, or 5.292 times 10 to the negative 10th meters. So there's a lower limit as to how close you can get to the nucleus without being absorbed by the nucleus. That's basically what Bohr was saying. Any energy above the ground state is called an excited state. An excited state has more energy than the ground state. It is further from the nucleus, and so as the energy increases, so does the radius of the orbit of the electron. And at the same time, the electrostatic attraction of the electron to the nucleus decreases. So going from the ground state to excited state is called absorption, and it involves a black line in a continuous spectrum. Going from an excited state to a ground state is called emission. It produces a line spectrum. Right, you have that single bright line. And the emission lines are what we see in the spectra of hydrogen. The Balmer series is explained by taking electrons from n infinity, so integers up to infinity, going down to n equals 2. That's so labeled on this diagram on the right. The Lyman series goes from n infinity to n equals 1. The Paschen series goes from n infinity to n equals 3. And finally, the bracket series goes from n infinity down to n equals 4. You can see in the energy level diagrams, that's what this is called on the right. Each line represents a different transition that has been observed. So all of those arrows, that's a different transition that we have seen with spectroscopy. Now, limitations, already said it, but it's back again. Bohr's model only includes one electron. It only works on hydrogen and ions of other atoms where you only have one electron. Once you get more than one electron, it does not work. He could not extend this model. Could not make it work. So obviously there's going to be someone else who's going to pick this up and make sense of it. Okay, so let's just try a calculation. We're going to calculate the energy change in an electron that goes from n equals 5 to n equals 3 for lithium 2+. So lithium 2+ will just have one electron. Okay, so what are we trying to calculate? We're going from a high energy to a low energy. And what type of transition is that? It's an emission. So how do we calculate energy change? Any type of change, we always go final minus initial. So we've got change of energy is going from 3 to 5. And we can plug in values, and then we realize that we can pull out a negative kz squared from that equation. And we can make negative kz squared times 1 over n3 squared minus 1 over n5 squared. And if we go ahead and figure out our z, we go to the periodic table. Lithium has a z of 3. And then we plug in the values and we solve. Okay. So once we have solved this, we get a negative number, negative 1.39 times 10 to the negative 18th joules. Wait, what? Negative. Negative energy? We can't get a negative wavelength. That doesn't make sense. But a negative energy does. Why is that? If you recall from what we were doing before, negative energy is energy leaving the system, and positive energy is being absorbed by the system. Emission is releasing energy in the form of a photon. So it has a negative sign, as it should. All right, to summarize, the Rydberg equation explained the hydrogen line spectrum by using an empirical formula. 1 over wavelength is equal to R infinity, the Rydberg constant, times 1 over n1 squared minus 1 over n2 squared. And n2 was always greater than n1. Bohr showed that you could derive the Rydberg equation using E equals h nu and E equals negative k over n squared. Where k is a constant based on other physical constants. In addition, he discovered that you could use it for any time, or like you have an ion where it only has 1 electron, so you just include the z number. And the radius of the distance that the electron is circling at is equal to n squared over z times a naught, where a naught is the Bohr radius. The Bohr model explains that electrons have quantized energies given as an integer. The lowest energy level is the closest to the nucleus, and it's called the ground state. Any other energy for the electron is an excited state. Going from the ground state to the excited state is absorption, and it involves a black line in the continuous spectrum. Going from excited state to a ground state is emission, and that produces a line spectrum.